So before I begin this video, I just want to do a quick plug for the NFT project that I'm working on with a group of people, and I think I mentioned in my community section a few weeks back. And so I just wanted to do just a quick plug. I won't take up too much time. I just wanted to show you the Twitter page. This is the Twitter account for the Particle NFT project. And so I'm just going to show you a little bit of what isn't going to be involved in that without giving away too many details. And so you can see here's an image of Buddha Brat, and Buddha Brat is going to be the final product of the NFT project. But in the interim, I am going to be generating NFTs with what I'm calling particles, which look like this. And these, of course, are iterative, generated via iterative feedback processes without giving away too many details. And so this is what they look like. And so this is what I'm going to be initially selling in the NFT project. Each particle is different, unique, and special. And in the end, we will end up generating Buddha Brats. Okay, so that is all I'm going to say for now. If you want to check out more particles and get more details and stay up to date on this project, you can follow me on the Particle. You can follow this project. It's not just me. I have a team of people helping me with this because it's a big project. And so I just want to do a little plug for that. I've been meaning to do this for a while. The time feels right now to start promoting this project, and hopefully, in the next few months or so, we will be able to, I will be able to give you more details. This video is a continuation of the Complex Numbers, the Biggest Blender series, and today we are going to take on quantum mechanics. To start this off, I'm going to play you an excerpt from one of Robert Distinti's videos on wave energy. Okay, so I highly recommend that you watch all of his videos on waves. Okay, he has a series of videos 1, 2, and 3, and each of them has different information. And so I highly recommend that you watch all of his videos on this, and you can even watch them before you watch this video. But they're, there's 3 of them, and they're 20 minutes long each, so it's going to take some time. And so if you want to watch his videos, you can look them up. I will try to remember to put them in the description, but if I forget, you should be able to find them quite easily. So here is the excerpt from this video on wave energy.
And so we find out there's 2 energy components: the height of the water and the velocity of the water, one giving potential energy, one giving kinetic energy. So all waves are basically a sloshing of energy. Energy goes from kinetic to potential, and from potential back to kinetic. And this sloshing of energy between the 2 types is what wave motion is. Okay, and that's what wave motion is, a continual transfer from one type of energy to the other as the wave propagates. And one of the interesting revelations we learned from this is that the vectors that contain the potential energy and the kinetic energy are parallel. Okay? In other words, in order for this piece of paper to move up and become the peak, well, this velocity has to be in line with where the height is going to be. So our velocity vectors and our height vectors are parallel. They're not orthogonal, but they're orthogonal, but it's a weird thing. Okay, although the energy vectors are parallel, they are orthogonal. And you're like, wait, what? A lot of people are improperly taught in college that perpendicular is orthogonal. If things are perpendicular, they're orthogonal. Well, that's true. If something is perpendicular, it's orthogonal. But orthogonal can also be 2 vectors in the same direction. And you say, well, wait, they're not perpendicular. How can they be orthogonal? Well, because you may not be able to add them. You cannot add the height of a wave to the height of the wave to the velocity of a wave. These are 2 different things. Height and velocity are 2 different things, like apples and oranges. So even though they're in the same direction spatially, they're orthogonal because you just can't add these two values together. And that's what orthogonal means. Orthogonal means that the two components are independent of each other. You just can't add them. It's like adding apples and oranges. If I have 2 apples and 3 oranges, I'll still have just 2 apples and 3 oranges. Okay, if I had 2 apples and 2 apples, then I can say I got 4 apples. You can add them. They're not orthogonal. And so we find that the energy at any point in the wave, if I pick the height and the velocity at any point in the wave, the energy is the height squared plus the effective velocity squared. And this is the effective velocity, which would be the effective velocity is square root of 2hg. And I'll show you how we take care of that to make this easier. All right, we already had the discussion on orthogonality. I'm not going to go through this. You can read this on your own. Put the pause on it. And the other thing we have to realize is that the height and the velocity are in quadrature. Quadrature means 90 degrees out of phase. So if this is the real wave here in the blue, the height mimics the actual height of the wave, but the velocity, if we model the velocity over time, the velocity is in quadrature, meaning that where the height goes to 0, the velocity goes to max. Where the velocity goes to 0, the height goes to max one way or the other. They're in quadrature. That's critical. All wave phenomenon have the energy components in quadrature. Okay? So that's critical revelation 2. In critical revelation 3, the energy neglecting loss is constant over time and space. And we're neglecting losses right now. So we're neglecting loss. So the energy is the height and the effective velocity squared. If you just take this squared plus 0, this squared plus 0, this squared plus this squared, you end up with constant energy or power or whatever you want to call it as the wave propagates. And so the anomaly with regard to light, and this was covered in the opening video, is that the energy components in light are not parallel. Okay, these are perpendicular in space. So that's a problem. Well, that's a difference, rather. They're not in quadrature. The energy components are in phase. The energy is not constant because here the energy is 0, here the energy is max. And so something is really wrong with this Maxwell's derivation of the plane wave equation. It doesn't match all the other wave phenomenon that we've studied so far. And the biggest problem is it violates conservation of energy because, as stated in the opening video, as the photon passes here, it's 0 energy. When a photon passes this point, it's got maximum energy. So you get a photon that blinks as it propagates. And this is not the model we use. Engineers use a e to the j 2 pi ft or other variants of Euler's model.
So the important point here is that what Robert Distinti is saying is that this is the formula that electrical engineers use. So electrical engineers use a to the e to the power of I 2 pi ft. So what is 2 pi ft? Okay, so when you do unit analysis on 2 pi ft using legacy unit analysis, standard unit analysis, 2 pi has the units of radians, so 2 pi radians, and frequency has the unit 1 over s, and time has the units of s. And the s's cancel, and you end up with a radian term, and radians are the units of angle or theta. So this is basically a e to the I times theta, and we've seen that before. So in modified unit analysis, in the unit analysis that I'm defining, pi ft has units radians per cycle. So 2 pi has units radians per cycle. So 2 pi is 1 complete cycle, and the units of 2 pi is radians per cycle. In modified unit analysis, the units of frequency is cycles per second. So I explicitly have a unit for cycles, which I depict here as a delta, as a del symbol. And so these are the units of frequency, and of course time, as usual, has the units of second. And so the seconds cancel and the deltas cancel, and you end up with the units of radians. So my unit analysis is more complete from my perspective, in my opinion. My modified unit analysis is more complete than the standard unit analysis or legacy unit analysis, but we get the same answer that the units of 2 pi ft are radians, which makes this 2 pi ft converts to theta, to an angle. And so ae to the I 2 pi ft is really ae to the I times theta, which, as we saw before, is a times this two-dimensional matrix. So the cosine is on the forward diagonal, and the sine is on the minus diagonal. And we have, when I is positive, the sine is positive in the upper right quadrant and negative in the lower left quadrant. And when I is negative, sine is negative in the upper right quadrant and positive in the lower left quadrant. So what I'm going to be doing is I'm going to be looking through the theoretical physics in different fields and looking for an I term, something that has I in it, and I'm going to replace I with this 2 by 2 matrix. And when I see something that looks like ae to the I 2 pi ft, I'm going to be replacing it with the 2 by 2 matrix version, as you can see here. So according to Robert Distinti, this is the wave equation. It's a function. It is a formula that is used by electrical engineers to describe a helix wave. And when you take a vertical projection of a helix wave, you get a sine wave. And when you take a horizontal projection of a helix wave, you get a cosine wave. And as Robert Distinti points out in his video, this cannot be the correct model for light. This is in fact the correct formula for describing all light, all wave phenomenon, including light. Okay, but that's not what we're talking about today. Today we're going to be talking about quantum mechanics, and we're going to find the same thing. So we're going to start by looking at the time-dependent Schrodinger equation, which looks like this. And as you can see, there is the letter I in this equation, and this I stands for the imaginary identity. Okay, so what I'm going to be doing is I'm going to be replacing this letter I with the 2 by 2 matrix version of the letter I, of the imaginary number, which has a positive 1 in the upper right quadrant and a negative 1 in the lower left quadrant. And the reason I'm doing this is to gain insight into this equation, to gain insight into the interpretation of the constants of nature and the equation. And so when you do this, when you take a constant and multiply it by a matrix, you end up with something that looks like this. So here you can see that the reduced Planck's constant occupies the backward diagonal of a 2 by 2 matrix. Okay, and the thing that's interesting about this is we know that the backward diagonal of a 2 by 2 matrix is responsible for spin, it's responsible for rotation, and we know that the Planck's constant, reduced Planck's constant in theoretical physics, is associated with angular momentum. Okay, so it is associated with spin. So doing it this way gives us further insight into why Planck's constant is associated with angular momentum and more in particular spin, because the backward diagonal of a 2 by 2 matrix, and I learned this in computer science, is responsible for making things spin. Okay, if you want to make something spin, in 2 dimensions, you would use a 2 by 2 matrix, and the backward diagonal that has positive sense here and negative sense here is going to cause a rotation in a 2-dimensional plane. And of course, if you reverse the sense of these such that you have negative here and positive here, it is going to generate a spin in the opposite direction. So if the positive here and negative here was causing a counterclockwise rotation, then negative here and positive here is going to create a clockwise rotation. So that takes care of this part of the equation here. And so next we're going to deal with this symbol here, which is the symbol corresponding to the wave function. But before I do that, I just want to show you something that I found that I believe is part of the cause of the confusion with quantum mechanics. Okay, so here they say, take the time-dependent Schrodinger equation, which I just showed you, okay, which has positive in the upper right quadrant and negative in the lower left quadrant of the 2 by 2 matrix, okay, and then take the complex conjugate on both sides. So the complex conjugate of, so basically minus I, which is right here, is equal to this 2 by 2 matrix, which has -1 on the upper right quadrant and +1 on the lower left quadrant. Okay, so we can replace -I with this. Okay, and then of course if you multiply h through, this will be -h and +h. So this is the complex conjugate on this side. And so then they go on to say, but we can write the last equation by inversing the direction of time. So instead of taking the complex conjugate, what they do is they reverse the direction of time, okay, where t prime is equal to -t. And it says, it is a strange idea, isn't it? Well, yeah, it is a strange idea to recommend or suggest that we can reverse time. Okay, and then they go on to say, or someone goes on to say, intuitively, complex conjugation of a wave function describes the time-reversed wave function traveling backward in time. Okay, so, but this is not the case. So the complex conjugate is not equivalent to going backward in time. Okay, if you look at this wave function here, let's say you're standing over here on the right and you're watching this wave come towards you. Okay, so it is going to be spinning. You're going to see the spin in a counterclockwise direction, and you're going to see the wave coming towards you. But if you stand behind the wave, and if you're looking this way, of course you can't see a wave moving away from you, especially not a light wave, but if you could see it, it's going to look like it's spinning in the clockwise orientation, and it's going to look like it's moving away from you. So it's going to look like a time reversal of the wave, but the time is still going in the same direction. You cannot go backwards in time. Yes, you can reverse a movie and have something look like it's going backwards in time, and that's what's happening when you stand here. The wave is spinning, the helix wave is spinning counterclockwise, and the wave is moving towards you. And if you are standing here, the wave is going to look like it's going, the helix wave is going to look like it's going clockwise, and it's going to look like it's moving away from you. So yes, it will look like a time reversal, but really the complex conjugate is more, so the complex conjugate of a wave function is more intuitively thought of as a change of perspective of where you are relative to the wave motion. And so I think this is a cause for some confusion in quantum mechanics, giving the false impression that in the quantum scale, things can go backward in time. No. In reality, what's happening is the phase is going in the opposite direction, and you're looking at it from a different direction. And so I think the complex conjugate is more intuitively thought of as a change of perspective rather than a reversal in time. So I'm going to leave it at that for now. I think this is enough for one video. The point I want to make is how we can use the 2x2 matrix format of complex numbers, and in this case the 2x2 matrix form of the imaginary number I, to try to gain insights into the complicated equations that we see in theoretical physics that are potentially being misinterpreted because we're not using the 2x2 matrix format, which gives us a clear understanding of what the imaginary component is, which is the backward diagonal of a 2x2 matrix. So I hope you're having a good day, and I will definitely be back.